All right, time to move on to numeric to categorical relationships. So let's keep using our insurance data here. And recall that we've got a variety of both numeric features and categorical features, sex, smoker, and region. We're still sticking with charges as our label. That's what we're trying to explain or predict. So we want to look now at the relationship between these categorical features with the label. Now, as a result, because they're categorical, we can't use our same techniques as with the numeric features. We can't create a scatter plot. There's no way to plot a word on a numeric chart. So we can't create a correlation either. The formula for correlation doesn't work because it involves the difference between a mean and an actual value, and so that won't work. So we're going to use a different test called a one-way ANOVA and a t-test. So I made this little visualization just so you could realize the way to estimate the relationship of each feature on the label is to use the appropriate formula or statistical test for that type of data. Another term I want you to be familiar with here is the word groups. So I often confuse this when I had my Stat 121 class, when they use the term groups or nominal variable and all these different things. I didn't quite follow what they meant. We use the term group to refer to the unique values of a categorical feature. So because sex has two values, male and female, there's two groups, the female group and the male group. Then there is smoker, yes and no, region, 4 groups. Rather than plot a scatter plot of values like we do with numeric features, what we need to do instead is divide up a categorical feature among its groups based on some numeric feature like charges. So in other words, what we want to do is look at all the charges for females and all the charges for males, and then see if the mean is significantly different from each other. That's how we tell if there's a relationship between a categorical feature and a numeric label, if the difference in means among all the groups is significantly different. It's very easy when there's just two groups, only two means to compare, and the t-test is used when there's only two groups. Actually, we can also use the one-way ANOVA. It'll give the exact same result and the exact same p-value. Yep, we still get a p-value just like we did with the linear regression equation to tell us if the resulting test, the F or the t-test, is statistically significant, which would mean that, yes, we expect to find a difference among means the same with future data as we do with the data we find here. Anyway, we use the one-way ANOVA when there's more than two groups, like in the case of region. And then we can use the t-test to look at individual pairs, like compare northwest to northeast, or northwest to southwest, or something like that. So that's how we use these two. Again, just know that when you hear the term group, it's referring to a unique value of a categorical feature or variable here. All right, so let's start with the t-test. Here are two histograms. We've taken we'll assume this is some numeric feature. It's not actually charges because I think I just made up some data here for this to give an example. But we get two histograms and we take a categorical feature and we divide it among its groups. And then rather than having one histogram for charges or for smoker, because we can't do a histogram for smoker, we can just do a count of yes and no. But what we do is we do a histogram for the numeric feature that we're comparing or relating smoker to. Let's assume this is charges. So we do a histogram for charges, but we separate it up into two histograms, one for each group of the categorical feature. So this is one way to now look at the distribution, and this line represents the mean. So the goal here is to determine the way we determine whether or not there's a relationship between each categorical feature and the label is whether the mean of the label is different for each group of the categorical feature. So are the smokers significantly different from the non-smokers? Okay, it's actually pretty straightforward, and this formula might look scary, but it's actually not that bad. All we do is we go through and take the sum of, we take the differences in means between the two groups. So let's say this is x1 and x2, and we divide that by the square root of the standard deviations, or standard deviation squared divided by the number of cases. Add that together, square root of the whole thing. That gives us our t-test score. The t-test score then has an associated p-value with it that depends on the number of samples. And we'll get all of that automatically from a tool from like Tableau or Excel. So the t-test has a few other assumptions. This variable, this equation changes slightly depending on whether we want a one-sided t-test or a two-sided t-test. What does that mean? Well, a two-sided t-test, we're basically checking to see how much of these histograms here cross over each other. Now, a two-sided t-test assumes that we don't know which side the smoker and non-smoker is going to be on. So if this were charges, we have a good idea that smokers cost more money than non-smokers. Clearly this isn't charges, it's just hypothetical here, but because here it shows smokers are smaller. But we have a good theory, and there's enough research to say that, yeah, smokers have more health problems. Therefore, we know that smokers aren't going to be here, they're going to be on the other side. They're going to be higher than non-smokers. In other words, we know which tails are going to cross over. It's not going to be this tail, or, well, in this case, it shouldn't be these tails, it should actually be this other tail. If we have a theory that tells us which mean should be higher than the other, then we choose a one-sided t-test. If we don't have a theory and we're just exploring or guessing, we choose a two-sided t-test. The implication is, in a one-sided t-test, it's easier to get a significant p-value than it is on a two-sided test. So I'm not going to go into the differences in the formula based on whether it's a one-sided or two-sided test, so we're going to let the program handle that for us. Instead, let's go to Tableau and figure it out. Let's start by creating the visualization first. So let's go to Tableau. Let's make a new one here for, let's do, since we're on the topic of smoker, we'll start with that one. Smoker bar. So whenever we have a categorical to numeric relationship, we are always going to, let's see, we find smoker, and then charges. We're always going to create a bar chart. Now in this case, it made it a horizontal bar chart. I don't think I like that very much. I'm going to switch it to a vertical one. Honestly, it doesn't really matter. You can choose either one. So let's look at our average insurance charges here. Actually, this isn't average. Look at it, 9,000K. This is clearly doing a sum of charges. So let's change that. We don't want to compare sums because if we have more of one than the other, I mean, a sum only works if we have the exact same number of non-smokers as smokers. So we'll never use sum. Just go ahead and always, when we're doing bar charts, change it to an average. That looks a lot better or more accurate. So here is the average charges for non-smokers, average charges of smokers. That is huge. All right, so how do we then, actually let's continue to use our data exploration report since we've been doing that, and that'll be your deliverable from this phase. So I'm going to come down here past my scatter plots, and you might even create, well, it's up to you. You could subdivide these sections into the numeric to numeric versus categorical, but it's up to you. I'm going to just make one for smoker, give this a heading 2. Let's go ahead and write up our hypothesis. We're on to H4 now, I think, and I think we can say with confidence, based on mountains of prior research. If you want to, you can add some citations here. I'm not going to right now. We expect that smokers will cost more than non-smokers because of the many known risks to, lung cancer and other issues. I think that's sufficient for this one because there's not much more about it than that. There's really no reason smoking would have any good effect. So let's now go back to Tableau. Oops. Let's copy this chart, but I don't like fit height. No. Fit width. I don't like that either. Standard. You know what I might do is just move this. Nope. Didn't mean to do that. There we go. We don't need... Actually, this might be one case. What I'll do instead, this might be one good reason to use a horizontal chart because it'll fit better in my book or my report. Yeah, it's still really small, but you know what? That's okay. I'm trying to be quick here. Let's go ahead and copy. Oh, come on. There we go. Copy image. I had to be right on one of in the plot area. Copy. Let's paste that in there. What I want to do here is give them the mean. I wonder if there's some describe feature on here that I can use. Explain data format, drop lines, copy. No, doesn't look like it. I'll just hover over and grab average of charges 84.34, mean of non-smokers 84.34, mean smokers 30. What was it? 32.050. 50. Okay, and my t-test score and my p-value score right here. So how do we generate those in Tableau? Okay, so back in Tableau, I'm going to show you a couple of ways to calculate a t-test. Tableau handles a t-test okay, but it's a little more complicated than doing it in something like Excel, so I'll show you Excel as well. Tableau has made it possible to pull in Python and R code using TabPy and other server-like environments. However, the point of this course is to keep it simple in these point-and-click tools. So rather than do that, I'm simply going to show you this somewhat more complicated way in Tableau, although it's not too bad, and then how to do it in Excel as well. So first of all, in Tableau, what you'll need to do is divide up charges based on smokers and non-smokers. The way we do that is go down here and right-click, create new calculated field. Now, if you don't see these functions over here, you likely just need to click this little arrow that pops it out and expands it. And call this, I called mine charges. I'm going to close this out and show you the one I've already created. Here's charges smoker. I'm going to edit this one. So I call it charges smoker, and here's my logic. Now, if you have some programming background, this will look very familiar to you. If not, don't worry a bit. This is easy to understand and implement here. So if, then, else, null, end. These are key words that mean something in the Tableau calculations. They have their own simple language here to do these Tableau calculations. So the logic here is that if, and then this is the smoker column. So it's going to run this code line by line for every record in the data set. It's going to say if the column called smoker has a value of yes, then the value that goes into this new field we're creating should be the value of charges. So put charges in charges smoker if smoker equals yes. So in an if statement, anything between the if and the else is going to get processed if this conditional right here, we call this a conditional, is evaluated as true. So an if statement uses a true-false criterion. Smoker equals yes, that's either true or false. If it's false, then it'll go down to else and process whatever is between else and end. In that case, it just means put null or put nothing in the charges smoker column. So let me show you what that resulted in here. As I scroll across, I'll go to charges smoker and non-smoker right here. So you can see in this case, it pulls charges in, not smoker. That's the part that students get confused on. I'm looking at a bivariate relationship between charges and smoker. So to do that, I want the value, the numeric value of charges in these columns if smoker is yes. So here's the smoker column right there. So you can see yes, then a bunch of no's in a row, then another yes down here below. Let me move that up. Yes down here. So you can see now over here I have a charges smoker there, a bunch of missing charges. Then here's the next one who is a smoker. These are all non. Okay, so make two new calculated fields for both charges smoker and non-smoker. Once you've done that, we're going to make another new calculated field. And just in case you want to see, here's my, let's see, non-smoker field, just like before, but instead of if yes, if no. And same thing. Then I'm going to make another new column, and I call it charges smoker t-test. So again, calculated field, new, call it charges smoker t-test, or whatever you want, I guess. And here's the logic. Now, to understand this, let's go back to the book, and let me show you the formula for t-test. All right, here it is. So we have the mean of one group minus the mean of the other group, and it doesn't matter what order you put these in. There is an order to them, meaning whatever order you put them in, your t will be either negative or positive. So the range of possible t's is negative infinity to positive infinity, but it really doesn't matter what order you put them in. And that's going to be divided by the square root of the standard deviation squared, which is the variance of one group divided by the number of cases in that group, plus the variance of the other group divided by the number of cases. So standard deviation squared for both of these. All right, let me show you how these are implemented. Let's start here with the numerator. Mean of one group minus mean of the other group. So let me go back to Tableau, and that's what I have right here. Average of charges non-smoker minus average of charges smoker. Divided by, this divide right here is this line right here across, divided by the square root, and that's what I have right here. The square root, oh sorry, right here, square root. So this square root function, it opens right here and I close it down here. Now I could put all of this on one big line like we can often do in Excel when we're working with formulas, but it's kind of messy and difficult to work with. So it made more sense for me to break it out, and Tableau ignores white space. It has no problem if you break it out like that. So here's my square root, and here's everything in the square root. Now let's make sense of that real quick. So again, now we're looking at what's inside the square root right here. So this first evaluation here, this is the standard deviation squared, which is also known as the variance, divided by the number of cases. Well, that's what we have right here. The standard deviation of charges non-smoker squared. So standard deviation starts here, I pass in non-smokers, ends there. My square, you can see, begins and ends all on the same line. Divided by, that divide by is the one right here, divided by the number of cases, or a count of charges non-smokers. So I then put parentheses around this whole term, which I probably didn't need to. I bet it'll still work without that. I'm just being a little bit OCD here. This plus sign right here comes from this one right here, so I'm going to add to it the same thing for the other group. So squared standard deviation of charges smoker divided by charges smoker. All right, that's my t-test, and once I have that, I'm going to go to a new sheet like this one, and I'm going to drop it here on text, and it'll just show me right here. Here's my t-test score, 32.75. Now, is that statistically significant? Well, I can tell you just because I'm familiar with t-tests, that's gigantic. Yes, it's very, very significant, meaning that the difference in means between these two bars is very big. However, how do we get an actual p-value? Well, there's a few ways. Let me show you how to quickly read a p-value table. Let's go down to 7.8 here to critical p-value tables. And I've got a table here for students' t-distribution, and I've summarized just a few examples, but I've also got some links down here to more complete tables and p-value calculators. So here's how you read these tables. Up here, this is our alpha, and to get the p-value, it's 1 minus alpha. So degrees of freedom is down the left. This tells us which row we should be looking at. Well, what is degrees of freedom? Well, if you remember from a t-distribution, it is each group, the number of cases in each group, minus 1. Well, that is basically, when we have two groups, it's the total number of cases minus 2 then. And we know there's 1338 cases, which means we have 1336 degrees of freedom, which means we're looking down here at this row where it approaches infinity. So we have way more than 100. And we often do that. I think in most data science tasks, we're working with a lot of data. And I think it's usually pretty rare that we're working with some of these smaller numbers. So it's okay just to go straight down here most of the time and look at these values. So what we want to find is the largest t stat here that is smaller than ours. So we have 32.75. Now, okay, it was negative 32.75, but just ignore the negative because this is considered an absolute value. The highest one they have here is 3.09, which means that it's significant, that our p-value is less than 0.001, because remember this is an alpha, so a p-value is 1 minus this. So what I'm going to do is go back to our document, or more accurately I should call it our data exploration report we've been working on, and I typed in here my p-value is less than 0.001. Now if you want to get an exact p-value in there, kind of like we had, did we have? No, if it gets really small, it just round it on the other ones. But if you want to get a more exact oh yeah, like these right here, see these higher ones? We can get an exact p-value. And that's what these links are for back in the book to right here. We've got some more complete distribution tables, also some t-test p-value calculators. I'm going to click on this one. I'm going to click on that one more time here. All right, so degrees of freedom and t-value. This website's from a guy I did my PhD with. He has a bunch of online free calculators here. He's a nice guy. So degrees of freedom, the formula for degrees of freedom for t-test is the size of each group, smoker and non-smokers, minus 1 for each. So rather than calculate the number or count the number in each group and minus 1 from each, let's just look at the total that we already know is 1338 from our data description report, and minus 2 from that. So it's 1336. Then our t-test score was 32.75. Well, it's negative, but it'll be the same either way. Hit calculate. Our p-value is so small that they just rounded it straight to 0. They wouldn't even give us one, which is understandable. The way programming languages work, there's only so many digits that you can fit in a bit of memory, and there's just too many zeros to even put in an actual number there. So we're going to leave it the way it is. And what I want you to do next is come back here to the data exploration report, and I want you now to, let me put this in. Let me show you what I wrote here. In summary, smoking has an extremely large effect size, and that's based on the t-test score being very large, and a significant p-value. It is a strong indicator of insurance charges. Probably our largest one. And later at the end of this, when we're done analyzing all the relationships, I want to summarize all these in a table, which is often a good practice. So what I want you to do next is do the same thing for sex. We've got female and male, and I'll show you what I put here first. I added my thoughts on this. So prior research has shown mixed results on whether women or men have greater medical costs. For example, you can put in some citations, but I've actually looked at a bit of this research, and it says, for example, while it's possible for women to incur maternity costs, men are known to have greater risks of heart disease and other factors. Therefore, we propose an exploratory hypothesis for the role of sex. Now, in more detail, basically when men and women are younger, there's really not a difference, because women, that's when they often will have kids when they're younger, and so they're offset by men's greater risks. But as we get older, men usually have higher costs. But anyway, I'm just going to leave this as an exploratory hypothesis by saying there's no difference or there is a difference. Speaking of which, we ran a one-tailed p-value up here. I didn't show you how to handle a two-tailed p-value. So go ahead and see what you can do on this one, and I'll show you how to handle a two-tailed p-value on sex. So go ahead and create the chart, create the new columns, run the t-test, and then come back and let's see how you do. All right, I'm going to assume you've done that, or you didn't, and you just want to move on and watch me do it. So here's what I've got. I've got my bar right here that shows that men. Let me zoom in a bit. I didn't take the time to I should have made these axes bigger, but that's okay. It shows that men cost more than women, and we want to find out if that's significant. Here's my means for each. I got a two-tailed t-test, or a t-test of, actually, really this tailed, I should put it here on the p-value. That's a more appropriate place to put that. It's the p-value that's based on a two-tailed test. T-test of negative 2.101. And I show that that's less than 0.05, and the exact number is 0.038, well, 358, you can see right there. So in summary, gender appears to have a significant effect on insurance charges, but we know that the t-test statistic is much lower than that of smoker. So I might actually say, notice that the effect size is much lower than smoker, and I can say that because I use the same test on both of them so that they're comparable. My t-test of 2.1 here is way smaller than 32.75. So let me show you my code. Back here in Tableau, I've made my male and female charges here, so you can see them. Here's where I've got them right here: female, male, insurance charges for each. Then I did my t-test edit. Looks like this: female minus male, square root standard deviation, or the square of the standard deviation for female divided by the count. Same thing for male. That's what gave me my t-test. So let me pull this one out and pull that one in, or put that one in. There's my negative 2.1. So to get the exact p-value, let me show you a couple of ways. So first, let's go to, I'm going to go to this another t-distribution table right here. I like this one. Here's our probability, our alpha, and they even put in here the one-tailed, two-tailed p-values. down here I have my degrees of freedom, and I simply go and find, okay, where's my 1336? Well, 1,000's pretty close, and it's barely different from infinity, which is what this is representing here. So I'll just use, I'll use the one that's 1,000. So I find where's closest one to 2.1, or the highest one that's less than, it's this one right here. This is higher than my 2.1, this one's lower, so I go with this table. And I scroll up, and it says if you're doing a two-tailed test, your p-value is 0.05, which is basically always double the one-tailed test. So that's where I came up with this p-value of less than 0.05 right there, two-tailed. So then to get that score, I simply went back here and put in my 2.101 and calculate. And this time, because it's a much smaller t-score, I can actually get a more accurate or specific p-value score, and that's what I put in. All right, well, let me show you how to do this now in Excel, in case you don't want to have to put those together. So I'm going to open up insurance.csv, which you can get from earlier on in the chapter, and here's my data. So what I'm going to have to do here is insert a table over the top of it, sort by sex, and then I'm going to grab charges. Not all of them, let's do a filter here. Let's filter by female, or either one first, doesn't matter. I'm going to grab those, copy. I don't even have to copy paste them. Here's a quicker way to do it. I was going to make two columns just like I did in Tableau, but I think it might be easier just to do this. We're going to use an equals t-test formula. And the first array means a list of values is going to be all of the charges. So again, it's not sex. I'm not grabbing the sex column. It's the charges column until I get down to the bottom. Let's see here, this table, which I think is Control-Shift down. There we go. And then it wants array 2, which is going to basically start after that. I'll have to unfilter my table, but it'll start at 13. Actually, 664 to 1339. I'll unhide the table so you can see that's where it is. And then tails. Well, we're going to do two tails because we're exploring. And lastly, it asks for a type. Well, there are 3 different types of t-test. Well, actually, there's a lot more than that, but sort of. But the formula that we've been using is for a particular type called a two-sample equal variance. In other words, we assume that the distribution of both of them, both groups, are the same. So that would mean looking at the histogram to see if the shape is the same for men and for women. So we'd have to divide up the histogram by both. Well, let's double check that. Let me show you how I do that. Since Excel brought it up, I'm going to put in 2 there, and then close off that parenthesis and hit enter. And what Excel gives you back is actually the p-value score, not the t-test score. So I guess if you want the actual t-test score, you can do that in Tableau. I'm okay if you want to just give me the p-value and say that you did a two-tailed t-test, assuming equal variance, which is what the formula, that's what this formula back here in the book assumes, an equal variance. Well, how would you test? You could test, sorry, as I get to it, this formula assumes equal variance. So you could test it by just looking at the skewness, by dividing it with both. I'm not going to force you to go in this level of detail for this class. You can talk to your instructor if she or he wants you to, but what I would do is simply go back to the chart where we have the histogram for charges, and I would add gender or sex here as, let's see, yep, that'll work. Add it here to columns, and then it gives me one for female, one for male. Those histograms look really close to each other, and I would say that's really close to equal variance, and I would say that we met that assumption fine. Therefore, in Excel, back here, we do want to use number 2 for the type. So let me show you your other options, though. A paired sample, number 1, the formula is slightly different. That is when you have the two groups are not independent. it's, for example, the same people measured twice, one time and then another time later. Two sample unequal variance means we can't assume that the distribution of both is the same. That one of them, the histogram of one group would be much different than the other. And as long as you can eyeball and they look roughly the same, then I'd say it's close enough. But if one of them was like a perfectly normal distribution and this one was right skewed, then I would say no, I'd use the test for unequal variance. But anyway, that's how you do it in Excel. All right, time to move on to ANOVA. So now we have the case where there are more than two groups. We have this. We've got 4 with the feature region. The concept is the same, nothing different than we're doing before. We're trying to estimate the difference in means among all groups. So maybe every pair, green versus blue, green versus red, green versus orange, blue versus red and orange, red versus orange, divided by the variance within each one of these, how spread out each one of them is, to see how much they're all crossing over. So the formula is a bit more complicated, and it's truly a pain in Tableau. It's a lot easier in Excel. So what I'm going to do is show you Excel first, in case you want to stop the video after that and say, I'm good, I don't want to go into the Tableau version, but I will finish with the Tableau version after that. So let's start with Excel. And to do this, we will have to sort by region, A to Z, and I am going to take off this filter, which I forgot to do before. And let's grab all the charges, and I am going to filter once again. Let's do this one at a time. Deselect, let's grab Northeast. Okay. Oh no, not that one. I want to copy charges. Thank you. So I'm going to come over here. Paste. Northeast, Northwest, Southeast, Southwest. Okay, let's filter now on Northwest. Now, notice a bunch of my Northeast just went missing. That's because it hid those rows when it did this filter right here. So I've only got a few of my Northwest right here, or Northeast, because there was a lot more Northeast than there was of anything else. Anyway, Northwest, paste those in right there. Let's now get Southeast. So you might be saying to yourself, this is the easier version. Yeah, believe it or not, this is easier than the way Tableau makes it. So Southeast and Southwest. All right. So I'm going to get rid of that filter. If you want to, we can bring all these columns back up to the top, cut and paste real quick. Okay. All right, to run our ANOVA, you're going to need the stats package. So you have to go to File, Options down here at the bottom, and Add-ins, and down here at Excel Add-ins, click Go. And you want to check Analysis Tool Pack. Make sure that you have that add-in. Hit OK, then come here to Data, and over here you'll see Solver under the, Data Analysis under the Analyze column now. You may not see Solver, right? That's an add-in as well that I use sometimes. So click on Data Analysis and go to the top, ANOVA Single Factor. That's a one-way ANOVA. So hit OK. It says, what's your input range? Well, I'm going to come and click here, including my labels. Go all the way down. It doesn't matter if you go all the way down. I just got to make sure we cover that row that's bigger. So, there we go. Give me K through N. That'll work. Check the box labels in the first row. Output range. Where do we want to print out the output? Once you click that, make sure you click in this box. It's kind of a weird tool. It leaves your cursor back up here, and it'll change that if you don't click in this box before selecting a cell. So let's take it back to the top. Somewhere around here is good. I'll hit OK. And here's what I get. So let me spread some things out. And let's match it up to this formula I've put back here in the book. So here's our formula. A one-way ANOVA, we have to make several calculations. We have to first come up with the residuals, the sum of squared residuals. This is just like we did in the scatter plot to come up with where the fit line should go. So this simply says calculate for each group the mean, which is right here, x bar. Let me make this a bit bigger and easier to see. All right, we need to get the mean for every group, k is groups, and then we want to take the actual value of every record from the mean, which is what a regression line does, right? It's the difference between the plot and the mean. And then because some are negative and some are positive, we have to square that so they don't cancel each other out. And we're going to do that for every group k and add all of them for each group together. That's our between groups sum of squares, residuals. To do the same thing within group, we're going to take the, well, we'll get to that one in just a second. But this is basically the mean of one group minus the mean of all groups squared. And we sum that up across each individual for each group. Total, we don't actually need to come up with our f, so I'm going to skip that one for now. But this produces a sum of squared scores for between groups, which tells us the difference between the means, and then within groups, which tells us the shared variance. So again, between groups is the difference between these bars. Within groups is the variance within each one added together. Once we calculate those, we then need to normalize them by the degrees of freedom, meaning by the number of groups there are and by the number of people within each group. So we take that score and simply divide it by the degrees of freedom to get this mean squares between, mean squares within. And then our f-critical score is simply 1 divided by the other, and we calculate a p-value for the f-score. So Excel did all that for us, thankfully, which is why we like the Excel version, and it's given to us here. Sum of squares between, within, these are huge numbers because we're dealing with money or charges in the thousands. Then we have our degrees of freedom. There's 4 groups, so it's 3. For within groups, it's a total count minus number of groups, so 1338 minus 4 groups. Then here's our normalized, our mean sum of squares, so it's this divided by that gives us this divided by that gives us this. Then f-score is simply this divided by that. And it went ahead and came up with a p-value for us and everything. So I'm going to go ahead and put that back in the f and the p-value. I'm going to go ahead and go back to our data exploration report. And here's my region. I wrote up, we have no theory regarding the effects of region, therefore we'll simply explore regional effects. This is common. Usually a measure of something like region we use to capture any other variance or control for any other variance that we just don't have in the other measures. For example, with insurance charges, there could be something about the elevation of different regions that causes more or less skin cancer. There could be cultural dietary patterns that cause more or less problems in different types of health issues. So this is usually an exploratory hypothesis. Here's my bar chart. You know how to make that. Here's my means, which you can get from either Tableau or Excel. Also gave them to me right here, my averages. And then lastly, I'm going to go ahead. I put this full table in here. I was going to build it out, but I actually changed my mind. Let's keep it. No, I'll leave it there. We're going to fill this out in the Tableau version. But one-way F, I'll put right there. And I think I'm going to round that up to 2.97. Probably bold that. And then my p-value was right here. Oh, and it put it down to a different line. No problem. Nope, I don't want that. Sometimes I have to do a paste special and just do text or unformatted text. There we go. P-value, I'll put 0.31, call that good. So in summary, I'll put this down here. There is a significant effect of region. However, most of the difference is in the southeast region, which has which exhibits greater insurance costs than the other regions. Now, before I go on and show you how to do this in Tableau, let me bring up an important point. If you wanted to, you could say, well, okay, based on this bar chart, northwest and southwest, the west seems to be pretty consistent. The real difference appears to be in the southeast. Let's just do a t-test and just see if this one and compare it to each of the others, see if it's significantly different. You know, there is enough extra charge in the Northeast, we might be interested in that as well to see if there's a difference. So you could run individual t-tests on just pairs of these groups. Now, I'm not going to ask you to do that for the data exploration report checkpoint in this chapter, but talk to your instructor to be sure in case she or he wants you to do that. But I'm not going to include it here in my report. If I did, though, I would put it before I came down here to my summary, and then I could mention in my summary. So let's do this. Before I go on and show how to do that in Tableau, I would suggest that in your report you come up with some sort of summary table. And in here, what you could do is include the differences or all of the different effect size measures. So what I'm going to have here is put 3, and I'll show feature. And we know what the label is. It's always charges. So I'm going to put analysis p-value. And maybe one more. Let's go in here to layout, insert a column to the right, or maybe the left of that one. Let's put in effect size. So for example, in my first one, I have age. All right, age has a p-value. I'm going to grab, I think I'll grab the r-squared. Correlation would work too. I think I like r-squared on these though. So what I'm going to do is come down here and say, all right, in my summary table, let's bold these and say age r-square. There's my effect size, and the p-value is less than 0.001. And I'm going to go through and add this for each of them in there. So after age, BMI, same thing, grab r-squared. Looks like p-value is also below 0.01. Actually, that looked like I might have had a typo back there. R squared. I'm going to copy this one. Go and check out there in my report. I added 1 extra 0, not a big deal. It's already crazy significant. Anyway, lastly, children, let's go ahead and do this too. Grab my r-squared. And by the way, this table that I'm making, 1 extra 0 again, or maybe that was in there. I just forgotten. Anyway, children. One other point I wanted to make is that you might prefer to put this table at the beginning of the report instead of here at the end. In fact, I think that might be a better idea. I'm going to go ahead and move it up there and go up to the very top. The remainder of the report includes greater details on each relationship. All right. So I put my other 3 features in. The way I do this now, I have a different test now, t-test. So let's grab this, and I'll put up here smoker. I'm going to call this t-stat, not state. Now in this case, the effect size, it's measured differently, which is why it's important that I include that this analysis is different here. However, the p-value was still incredibly small, but that's not going to be true for the rest. Let's put in sex and region. These were significantly smaller, but they were both t-stats. Oops. And really, it doesn't matter that I put that negative in there. Same with this one. This one was less than 0.05. And I believe this one was the same. Oh, this one wasn't a t-stat. Sorry, this one was an f-stat. But technically, these are all supposed to be italicized. Sometimes you get lazy, and it's really not a big deal. So in here, the f-stat, let me just grab that one, was right here, 2.97. Okay. This is a decent bare bones data exploration report. And if you're doing the checkpoint at the end of this chapter, this would be a good format to turn it in and complete everything. You might add a little more right here. You could say, we find that all 6 features are worth including during the modeling phase. So basically, what we were trying to do is understand these relationships so we could narrow down or sort of reduce the number of features we really need to look at. Now, in this case, we only had 6 to begin with, so it would have been very simple just to include all of them in the modeling phase. But you often have, like I say, hundreds or even thousands. So what you want to do is automate this testing. So first of all, you don't have to do what we just did for every single one manually. This is a good reason to go in, if you have that many features, to learn something like Python or Julia to go through and automate the process of calculating all these stats. But either way, whether you have a lot or a few, this is a critical time to explore in greater detail. Something we haven't done yet, which there might be another video on in your chapter, is when you see something like this and you notice there's a clear problem, do we go into 3D, 4D, 5D, 6D charts to understand and drill further into that? Anyway, if I'm going to stop. For those who wanted to stick with Excel, you can quit this video. You're good to go. For those that want to see how to do the F in Tableau, I'm going to do that next. But again, that's only if you want to. So Tableau, here's what we have to do. We have to first, let me get rid of this. We have to first go through and create the column for all different values of region. And you can see I've done that here. I've got charges, northeast, northwest, southeast, southwest. But once you do that, you have to make another version of each called the residual. So charges, northeast, residual. So again, just so you remember, this was a simple if. If region equals northeast, then pull in charges. And that gave us the new column. What I'm doing here in the residual is calculating this sum of squares right here. I'm not quite able to calculate this score, but I've got to come up with the residual for every single cell or every single case, because Tableau doesn't allow you to mix aggregate and individual level analyses. Let me show you what I mean. So right here, I've said, okay, if region equals northeast, don't just put in charges, but calculate the squared residual, which is charges minus, and I had to manually calculate the mean for charges and plug that in. So I could get that from here in Tableau by going to, where is it, region bar chart, and I can see my mean here. Oh, I've got count. Let me change that to mean. Average. Here's where I got my mean from. So 13,406, I grabbed the one for northeast. For northeast residual, I made a new record called the residual, which is the actual value minus that mean. See, I couldn't plug in average of charges here because it won't let me do, it won't let me put an aggregate score right here that's going to be used for every single column or every single case. So I had to just plug it in manually, which is a bit of a pain. But anyway, all right, so squared residual. Let me show you what that gives me. I did that for all of them. There's northeast residual, and then northwest. Remember, I'm using the mean of northwest, not the mean of northeast. So I had to change that to the northwest mean. And let me show you what that looks like when I got it here. So charges, here are all of my residual scores. So because I'm squaring the difference, see, they're gigantic, they're huge. That's okay, we kind of know that because in Excel when we did this, we could see that our sum of squares were pretty big numbers. Once I do that, I have to actually normalize that score. So first of all, let's find out what I've got here from those. I'm going to go to this blank sheet here and just pull all of them in onto the text here so you can see what they look like. And these are huge numbers, of course, but that's okay. That's to be expected, because if you remember when we did this in Excel, these numbers are pretty gigantic too. That's because we're dealing with, thousands of dollars here. Anyway, what I want to do next is calculate these two formulas, the between group sum of squares and within group sum of squares. So these the formulas for these are pretty simple now that we've got the columns that we need. So let me go back and show you exactly what these mean here and translate them back and forth for you. So I'm going to actually pull these out. I don't need them anymore. Let's start with the within, because that one I think is pretty simple. So formula for within. Notice that this is the same as what we had in Excel right here. 1947. This is just scientific notation. Plus 11 means move the decimal place 11 places that direction. I always get a couple students that it's easy to forget that from high school if you haven't run into numbers like that before. Let's change it back. Oh, not there. Almost change that back to a number. But we don't need any decimals. Okay, so that number right there, that's the same as what we have right here in Tableau, and here is the formula for it. It's basically just adding up the residuals for each. So this part was easy, but I couldn't add these together. I couldn't use the sum on these along with the formulas for each. You'll get an error. And you can try it out. If you want to try and combine them, you'll see what I mean. So within, back here, this formula is just basically saying we need to sum up those squared residuals for every individual within every group. And that's exactly what we've done here. So let's talk about sum of squared between. Now this formula is a little bit trickier, and it's actually not that bad though. So here we're trying to look at the difference between means across the groups. So between the groups, what's the total difference? So the bigger this number is, the more likely we are to find a significant effect, or the larger the effect size of region on insurance charges. So the way this one works is we need to get the sum of all the actual charges for a group, and then we square that sum and divide it by the count. So you might look at this and say, wait a minute, the sum divided by the count is not just the average? No, pay attention here. We're squaring the sum first before we divide by the count, or the number of cases in that group. Then we subtract from that the squared sum of all of them. So notice I'm using charges here. So this one, first of all, notice that I'm looking at the actual values, not the residuals. I use the residuals for the within sum of squares. For the between, I'm just looking at the actual values in each group. I square those, divide them by their counts, and then take that and add them all together and subtract from that the squared sum of all charges altogether divided by the count of all charges. So this is normalizing the differences among all groups by the total number of cases in the group. So hit OK. I'm going to pull this in also on text. That gives us our 1 million, or 1,300,000,000. That's the same score as what we have right here that Excel gave to us as well. And again, back here, this is just representing perfect. Okay. So back here, what we need to do next, sorry, what I meant to say was this right here. We need to now normalize these two scores by the degrees of freedom for each. So between groups, we want to normalize by the number of groups, and within by total sample size, subtract the number of groups to get the MSB and MSW. So let's do that back here in Tableau now. We're going to, let's edit these. I'll start with between, I guess. Edit, and now let's change that to be this whole thing. I'm going to wrap parentheses around all of it, so I can now divide by the degrees of freedom. So degrees of freedom is for a number of groups minus 1. Okay, so I think I'm just going to hard code this in 3, because there's not really a great way to automate that I can think of. There probably is, but it's not worth going into detail. I'm just going to put 3 in there, and now we're going to call this mean squares between. Changes it to 43358, and let's do the same thing for within. This one will be divided, but I wrap the whole thing in parentheses. This one is going to be divided by, it's the number of cases minus the number of groups. So that's 1338 minus 4, or I could just type in 1336 if you want, and change this to mean squares within. Okay. So let's make sure our numbers check out with Excel. I've got 146,007 for within. Yep, right there. And then 433,586 for between. Yep, right there. So lastly, our F, and I'm just going to go ahead and make this, I guess, a new calculated field. Why not? We'll call this charges region F. And this is simply going to be charges region between divided by within. Charges region within. Okay. Pull this out here too. 2.970. Is that what we got in Excel? Sure enough, once you round it up, it's 2.970. So to get a p-value out of this one, rather than create the formula for that, let's just go to a calculator online. So come back here to the group, to the book, and take a look here in the next section for p-critical tables. Again, this is just 7.8 here in the book. Scroll down, let me show you how to read a table and use a calculator. So to read a table, there's actually many different F tables because there's 2 degrees of freedom we have to consider. And as a result, we make a separate table for each level of P. So for example, this first table here says this is the, let's see, these are the P values when looking at, is it telling us what the alpha level is anywhere? Oh, we have that over here. Oh, this is nice. Okay. So this is the degrees of freedom in the numerator, degrees of freedom in the denominator. They actually, this one combined all tables into one, but it's one really long table. So let me show you how this works. So we have the numerator in ours is the number of groups. So that is the degrees of freedom, which is back here 3, and then the denominator is 1334. So, whoops. Okay, so numerator is 3. We're looking at this column. And the denominator, 1334, well, we're way past 7. So down here, here we go. We're still going. We might have to go quite a ways down to infinity. I'm guessing the last 1,000. We'll go to this one right here. So we're still here on 3 in the numerator, denominator 1,000. Ours was 2.70. So it looks like this is the one that is the largest, that is less than 2.70, which sure enough takes us over to a p-value of less than 0.050. And that sounds about right with what Excel gave us, right? It gave us 0.30, which is still bigger than the next alpha level. If you want to use a calculator, come back here, let's grab an F p-value calculator. It looks like this is also Dan Soper's. So numerator is 3, denominator is 1336. Oh, this is the F value calculator. I actually need related calculators. I need p-value for an F test. I'll update the link in the book to use this one. So 3, 1336, F value is 2.97? Yeah, I think so. Calculate. Oh, so his doesn't even go up past that one. So we're just going to put in 999, which is basically assumes infinity. All right, 0.310. Does that look like what we got in Excel? Yep, that rounds up to 0.310. So that's it for categorical to numeric features. We'll move on to categorical next.